Welcome to a lesson with Dr. Powell. Let's take a look at how a surface like this with a great divide can actually help us think about taking derivatives with limits. Well, this surface right here can actually be found by thinking of, see the z-axis here, that is altitude. By thinking of altitude, the z-value expressed as a function where the input is a coordinate point in the xy plane. So we could think of like this, the output is going to be for some kind of function where we're plugging in x, y. And the actual formula for this particular surface is sine x minus sine y, all divided by x minus y. This is a fraction that looks very similar to things that we have when we're taking a limit and getting a derivative. In particular, when we're taking the derivative of sine. What is the derivative of sine? It's cosine. You see this great divide? It is the cosine curve. It is the derivative. It is where this thing is not defined for this function. I've exaggerated that great divide where things aren't defined so you can kind of see it better and take a look at it. Now, that should make sense. Where x is equal to y, then you can't divide by 0, so it would be undefined. But actually, as x gets close to y, then this fraction should end up giving me a slope of a tangent line, or close to the slope of a tangent line, where I have 2 points that are close together on the slope of sine, and take the line between them. You know, x and y being values that I'm plugging into sine, and the outputs, and getting rise, so the top would be rise over a run. Yeah, it should give me that slope, and as x gets close to y, it should give me the slope of the tangent line, so it should give me cosine. The cosine as I'm taking a limit. Okay, well, how can this be useful? Let's take a look at when we're actually making the computation for the derivative of sine. We have the limit as a approaches x of sine of a minus sine of x all over a minus x, where x is like a constant in this limit, and a is the thing that's variable in the limit and it's changing. Hey, this is like saying, okay, I have like a comma x, and this coordinate point in the xy plane is getting close to xx, where this, the x stays the same, constant the whole time. The only thing it's, well, so this in the second coordinate stays absolutely the same. And the first coordinate changes, and we're heading in toward that guy. So it's kind of like we're heading to a particular point on the graph of the derivative, and we're heading to it by just the first component changing, but the y component here, which represents the second guy, doesn't change. So it's like we're heading to the limit this way. But couldn't we get to the same place by doing something else? Couldn't we head to it by going like this, in this direction? In fact, we could get to it by going in like any direction. Really, we should get to the exact same place. The reason being is because, well, this surface is a nice continuous surface away from where it's not defined. In fact, visually you can see a few things here. If I take a point on the graph of the derivative and another point, this point is close to something that's that's limiting to it, and something that's limiting to it. But these 2 points right here, you can make, because this is a nice continuous surface, if I drew these 2 points close by in terms of their xy coordinates, then these 2 points would be close by in their xy coordinates. But the z values between these 2 points are close, and so the z values between here and here are close, and between there and there are close, so the z values of here and here are also close. So that closeness between z values where the xy coordinates are fairly close actually gives us intuitively a nice way of thinking about that the derivative function itself is continuous. So we have continuity of the derivative where it's well defined, and that continuity helps us fill in continuously the surface. So, so that truly we can come into it from any direction. So, in particular, we could have come into this by swapping the a and the x by going like this, xa. All right, and then in turn swapping where the a and x's are in this expression. So we could say sine x minus sine a, and this should be pretty simple in this case to notice that when we swap things like that, it works great, right? Because well, essentially what have we done? To the top and bottom, it's like the same thing as multiplying top and bottom by -1. Yeah, let's cancel. It should give us the same limit. Great. And it doesn't give us very much additional knowledge or information in this case. However, it does in other cases. Let's take a look. Okay, so let's suppose that we want to compute the derivative of the function x times cosine of x. All right, we can set up a limit. Let's use a's and x's here. So let's suppose that we have the limit as a approaches x of a cosine a minus x cosine x. And all of that is over a minus x. Okay. Now, right now, swapping the a's and x's doesn't do anything for us either. However, it will in a minute. What we're going to do is we're going to think about this expression, the expression x cosine x, and split it up into boxes, where the boxes are not inside each other at all. They're separate pieces from separate pieces. And then we're going to kind of think about both parts as doing something differently. So it doesn't matter how I do this, what I'm going to do is I'm going to assign one of these guys to be variable, the rest constant for a minute. So the thing that's variable in this limit is a, and I'm going to expand this numerator here, a cosine a, and I'm going to subtract something, and I say this part I'm going to put over here. Okay, but before I put it over there, I'm going to put something new. I'm going to subtract something, then add by the same thing so they cancel out. So it's like I'm inserting 0 in the middle of this thing. I'm going to put 0 in between these guys. And the way I'm going to get it is, it doesn't matter which way I do it. I'll just say, instead of x in one box, I'm going to call a, and the other box I'm going to leave it as x. Okay, so since I did that, let's add by it, because I don't want this to change my fraction. So the net result is just 0. And then let's put the last guy right there. Notice that this, which is going to be a numerator, over a minus x is the exact same as this numerator. Why? Because the middle part is just 0. But then let's split up the fraction. So the denominator is a minus x over everything, but we can unadd the fractions, so we get that over a minus x plus that over a minus x. Now we're going to concentrate on the limit of this part and this part separately. Okay, so in particular, a is a thing that's changing, but I see lots of a's now in the top. Now, I would like to see as few a's as possible up here. And so what I'm going to do is I'm going to do a switch. In this case, I'm going to switch a and x. All right, but I should get the same limit from what we just described. So if I did that, what would we get? We'd have x cosine of x minus x cosine of a all over x minus a. And then we can multiply top and bottom by -1, and then let's just see what we have. So we have x cosine of a minus x cosine of x, and all of that is over a minus x. Now, if I were to factor out the x here, just out of it, now realize that a is the thing that's changing in the limit as a approaches x. Factor the x out, then we're left with, so we have x factored out, we're left with cosine of a minus cosine of x all over a minus x. Huh. This looks like something that will actually limit to the derivative of cosine, right? Yes, so that'll limit to that derivative of cosine, which is negative sine, and that'll be multiplied to x. So coming from this part, the first part right here, we're going to end up getting negative x sine x, because negative sine x is the derivative of cosine, which this right here in the calculation would yield, but then we're multiplying by x. That's what we got from the first part. The second part, it looks like we have just 1a, so that's kind of nice. In fact, we could just factor out the cosine x in this case. And factoring it out, well, that's nice. We have a minus x divided by a minus x. Those guys will cancel, right? And then we're left with just cosine. So then we have just plus cosine of x. Okay, so we just successfully computed the derivative of this in a limit by using this little switch property. Okay, by first we added something in the middle, a 0, and then we used the switching to help us. The switching doesn't just help us when we're multiplying two things, it can help us at other times. We'll go through one more example and then we'll generalize it into a rule.